Hello and welcome, student, to the proof of this theorem that we will use the density theorem of rational and irrational numbers to prove that for any real number x, if we are given any real number x, we can find a sequence contains only rational numbers. So if you have x, you can get a sequence q1, q2, q3, and so on. And this sequence will converge exactly to x. Similarly, we can take any number x and we can find another sequence, but this time it will contain only irrational numbers with the limit of this sequence will be x. So here we have irrationals and those irrationals will converge to x. So the idea to prove this theorem, we will only start with proving it with rational numbers. Similar proof would be exactly the same for irrational numbers. So what we have here is we are given x be any real number. We consider the following process, which contains a construction of rational number. So to construct a sequence of rational numbers. Okay, how this process will work. First of all, we will take my x here in the middle, and I will create this interval by doing x minus 1 to x plus 1. So this is a general interval. If you want, I can write it down here. This is the interval x minus 1, x plus 1. And of course, in any interval, we can find a rational number. We will call it q1. So we'll just find q1 here in this interval. Why this is correct? Because of the density theorem, that any interval contains infinitely many rational as well as infinitely many irrational. We will take only one of those infinitely many rational and we will call it q1. Of course, this has a meaning. If we just focus on this one, this means x minus q1 will be less than 1. So q1 and x are of a distance less than 1, and this is the first step in my process. I will call it n equal to 1. So if we have step number 1, I will find q1. Now I'll do the same in step number 2, but this time I will take the same interval x, but here I'll just write x minus half. I'll make it shorter, x plus half. Of course, what we will get in this interval, we will get x minus half, x plus half. So I will get q2 in this interval. So somewhere here, you will get q2, maybe here, but just illustration. Of course, don't forget that we have already q1 from the previous step. So we have q1, and now we get something closer to x. What do we mean by closer to x? It means x minus q2 less than a distance of half. So we are getting closer and closer to x as we move along. Now, if we do step number 3, will be the same idea here. So in step number 3, all what we need to do is this is x, and we will do x minus 1 over 3, x plus 1 over 3. So the idea here will get q3, q2, and here q1. That's how we get it. So we get closer and closer, and this is the same idea as we just said. q3 will belong to this interval. So this is a process to create a sequence. Of course, the sequence has to do something with the 3, 2, and 1. So this will be 1 over 3, and so on, so forth. We can continue in the same way by doing the same thing. If we continue the same way, what we will get eventually is something like this. For any n I give you, you will find Qn in this interval, x minus 1 over n, x plus 1 over n. Of course, if we do it here, this is x. So this will be x minus 1 over n, x plus 1 over n. And for any n, you must get Qn. Of course, remember that Q1 may be outside, Q2 will be outside, maybe inside, outside, and so on. Which means we are getting closer and closer to reach where we want to reach, which is this one. So the idea that x minus Qn less than 1 over n. That's the idea here. And that's how we will use. Now what's left for us is the following. We claim that this sequence of Qn converges to x. So finally, we claim that the sequence Qn converges to x. In order to prove this claim, we'll do the usual thing as always. We will let epsilon greater than 0 be given to me. And I will write my required step. So what is required from me? It's 3 things I need to do. The first one is I need to find capital N natural number such that if I assume that n is greater than this capital N, then the left hand side of x minus Qn will be less than epsilon. So actually this is a 3-step proof. Step number 1 here, to find n. Step number 2, to assume or take n greater than n. And finally, step number 3, to prove that the left-hand side of this inequality is less than epsilon. Of course, the only information I have about x minus is 1 over n. So I need to remember, how can I bound 1 over n using or given epsilon? So this will just get into our usual technique in analysis. If we have 1 over n and we want to deal with it with epsilon, we will invoke the Archimedean property. So by Archimedean property, give me an epsilon, you will find n capital in natural number such that 1 over n capital is less than epsilon. This is for sure by the Archimedean property. Now, this will take care of step number 1. I found capital N. The only information I know about capital N is 1 over n capital less than epsilon. This will take care of the first step. Now, the second step, as we always say, it's just an assume, and then I will start working on the left-hand side of step number 3. So step number 2, I will assume that given an n greater than n capital, which of course it means 1 over n small is less than 1 over n capital. If we just flip them, reciprocal of both sides, we have to switch the inequality. So n greater than n, it means 1 over n small is less than 1 over n capital. And finally, we have to work on the left-hand side. And this is the left-hand side. And hopefully, after we do many steps here, we'll get it less than epsilon. Let's see, what do we know about the left-hand side? The only information we know about the left-hand side is that whatever x minus Qn is less than 1 over n small. So just let's write it less than 1 over n small. And what do we know about 1 over n small is less than 1 over n capital. Why? Because of my assumption here. And what do I know about 1 over n capital? It is less than epsilon, and if you don't remember, this is the Archimedean property. And of course, this is by assumption. And of course, this one by the construction process. And hence, we prove that Qn converges to X. Of course, a similar argument, exactly the same steps, we can do it for the irrational numbers, and that we prove that for any real number, we can find a sequence of rationals that converge to that real